In our last video, we derived the expression of capacitance of a parallel plate capacitor when there is air medium between the two plates of the capacitor. In this diagram, A and B are the two plates of the capacitor. Here the plate A is positively charged. That's so there is an induced negative charge at the left side of the plate B or the inner side of this plate B. And any induced positive charge on the plate B is moved to the earth due to the earthing. See, the outer side of the plate B is earth. So, any positive charge induced in the plate B is moving to the earth. Now, in this video, we will derive the expression of the capacitance of a parallel plate capacitor when there is a dielectric medium. Here we have introduced a dielectric medium of thickness T, small t, between the plates of the capacitor. Let the dielectric constant of this dielectric medium be K. Already we discussed about the dielectric constant and its definition in our previous chapter, that is electric field and force. So, before starting our derivation, let us recall some basic ideas which we need for the derivation of the capacitance of a parallel plate capacitor when a dielectric medium is introduced between the two plates. See, already we discussed about the dielectric constant of a dielectric medium in our previous chapter, electric force and field. So, dielectric constant of a dielectric medium is a unitless and dimensionless physical quantity, and its expression is F naught divided by F or E naught divided by E, where E naught represents the electric field for air medium and E represents the electric field due to a charge for a medium having dielectric constant K. Similarly, F naught is the force between two charges when there is air medium between the two charges, or the medium between the two charges is air, and F is the force between the same two charges separated by same distance apart when there is a medium having dielectric constant K between the two charges. So, this is the definition of the dielectric constant or mathematical expression of the dielectric constant. Also, again, in our last video, we derived the expression of capacitance of a parallel plate capacitor when there is air medium between the two plates. See, this is the expression of the capacitance. C is equal to epsilon naught A divided by D, where A is the cross-sectional area of each plate of the capacitor and D, small d, is the separation between the plates, and epsilon naught is the permittivity of free space. Again, we also derived the potential between, or the potential difference between the two plates, that is capital V is equal to E into D, where E is the electric field intensity, strength of the electric field intensity between the two plates of the capacitor, and D is the separation between the plates. So, V is equal to E into D. Also, we know that E, or electric field intensity for a parallel plate capacitor inside the two plates, is equal to sigma by epsilon naught, or where sigma is the surface charge density and it is equal to charge divided by cross-sectional area of each plate of the capacitor. So E is equal to sigma by epsilon naught, sigma is equal to Q by A. So we can write that E is equal to Q divided by epsilon naught into A. So let us start our derivation. Let us consider a parallel plate capacitor with plates A and B separated by distance small d apart. Let C naught, as we will find the capacitance when a dielectric medium is introduced. So we will write the capacitance of a parallel plate capacitor when there is air medium between the plates as C naught, and for this we will write the capacitance as C, potential as V, electric field intensity as E, and here when there is air medium between the plates of the capacitor, we will write the capacitance as C naught, potential between the plates as V naught, and the electric field intensity between the plates as E naught. So let C naught be the capacitance with air medium in between the two plates. Capacitance with air medium between the two plates and already we derived the expression of C naught is equal to epsilon naught A divided by small d. Let us write this as equation number 1. Again, if E naught and V naught are the field and potential difference, between the plates when there is air medium then E naught is equal to sigma divided by epsilon naught, and sigma is the Q divided by A, so Q divided by epsilon naught into A, and V naught is equal to E naught into D. So these are the capacitance, electric field and potential when there is air medium between the two plates of the capacitor. Now when a dielectric medium having dielectric constant K and thickness T is introduced between the plates of the capacitor, then the thickness get reduced, then the air thickness get reduced from d to d minus t. See, now only this much space is filled with air, and the central region is filled with the dielectric medium having dielectric constant K. See, so this is air medium and this is also air medium. As the air thickness get reduced from d to d minus t, so the electric field intensity will also reduce, also the potential will change accordingly. So both the electric field and potential difference will change accordingly. See, here potential V is equal to E naught into D minus T plus E into T, where E is the electric field strength inside the dielectric medium and E naught is the electric field strength of the air medium between the plates of the capacitor. So, but we know that, let us write this one, where E is the electric field strength between inside the dielectric medium. Electric field strength inside the dielectric medium. So, but we know that, write this as equation number 2, but we know that K is equal to E naught divided by E. This implies E is equal to E naught divided by K. Okay, let us put this value of E in the above equation 2. This implies V is equal to E naught D minus T plus E naught divided by K into T. So, this is equal to E naught is common, D minus T plus T divided by K. So this is the value of V, or the potential difference between the plates of the capacitor when the dielectric medium of thickness T is introduced between the plates. So if capital C is the capacitance of capacitor with dielectric in between, then C is equal to charge divided by potential we already know this definition. So this is equal to, if Q is the charge of the capacitor, then this is Q divided by V. So this is equal to Q divided by E naught D minus T plus T divided by K. So this is equal to Q divided by, see here E naught is equal to Q by, E naught is equal to Q divided by A into epsilon naught into D minus T plus T divided by K. So this is equal to epsilon naught into A divided by D minus T plus T divided by K. Now this is equal to epsilon naught into A divided by, let us make it common, D as a common. So D 1 plus 1 minus T divided by D plus T divided by K into D. So this is equal to epsilon naught A by D, because this is the capacitance of the parallel plate capacitor when there is a air medium, divided by 1 plus T divided by K D minus T by D. So this is equal to, see, this is C naught divided by 1 plus, again T by D will be common, into 1 by K minus 1. This is the final expression. So C is equal to C naught divided by 1 plus T by D into 1 by K minus 1. Let us write this as equation number 4. Suppose the whole space between the two plates of the capacitor be filled with a dielectric medium, then this thickness T will be equal to D. So it is a special case. If the whole space between the two plates is filled with dielectric, then D is equal to, or T is equal to D, then T is equal to D. So putting this value in the above equation 4, this implies C is equal to C naught divided by 1 plus D by D 1 by K minus 1. So this is equal to C naught divided by 1 plus 1 by K minus 1. So this is equal to K into C naught. Okay.